This is our final video on our series on acid-base strengths. So in our previous videos, we had explored acids. Here we're going to talk about our bases. So when it comes to our bases, our strong bases are predominantly ionic bases, and most ionic bases are going to be strong bases. Primarily bases with cations from group 1 or 2A because they are ionic, they simply dissociate in water. So our strong bases, again, are ones with cations coming from group 1 or group 2A. There is no proton transfer involved here. We put that strong base into water, it completely dissociates. So if I had something like a sodium hydroxide, so group 1A cation, it's a strong base, we put it into water, it completely dissociates. Now these strong bases are because they have strong solubility. Remember our solubility rules, group 1 and 2A hydroxides are going to tend to be soluble. If they're soluble, they're going to dissociate. So when we're identifying our bases, again, we've got to know group 1 and group 2A. Those are strong. If it's not a group 1 or group 2A base, then it's going to be a weak base. Now with our weak bases, these are going to be predominantly ones that undergo proton transfer. And proton transfer requires molecular compounds. So in terms of our molecular bases are going to be weak. They don't dissociate, but instead accept a proton from the solvent because this is a weak process. It is reversible and therefore reaches equilibrium. So very similar to what we saw with our weak acids. We're going to have an equilibrium. And all equilibria can be described by a K. In this scenario, this is the K for the interaction of a base with water. We're going to call it a KB, or our base dissociation constant. So we can look at a generic base, B. We put that into water. The base is a proton acceptor, so it's going to take a hydrogen from the water, forming our BH plus and hydroxide. For that equilibrium, we can set up our K. Our K equals the concentration of each of my products raised to their coefficients divided by my reactant raised to its coefficient. So again, my water here, it's pure liquid, we are omitting it. So it's my conjugate acid times my conjugate base divided by my original base. Now, just like we talked about with acids, for acids, we said Ka was going to indicate the extent of acid dissociation. Here, this would again be the extent of dissociation. Or we could talk about the rate of proton acceptance. And if we're talking about, again, this dissociation in water, or here this ability to accept hydrogens, that is going to be our strength. So Kb indicates our base strength. Larger Kbs correspond to greater percent dissociation or greater acceptance of hydrogens, which indicates a stronger base. Smaller Kb corresponds to lower percent dissociation or a weaker ability to accept hydrogen, which indicates a weaker base. So we've seen very commonly the example of ammonia. We saw that the first place we saw our double arrows in this chapter. So we can write our dissociation or proton transfer equation. So we put that ammonia in water. The ammonia is a base, so it's taking a hydrogen from the water, forming NH4 plus and hydroxide. We are producing hydroxide. That makes it that Arrhenius base. We're doing so by accepting hydrogen, making it the Bronsted-Lowry base. Either case, it's a base, so we're describing that equilibrium by a Kb. So Kb will be the concentration of NH4 plus times hydroxide divided by my original NH3. Now, when it comes to our weak bases, most weak bases are going to be organic derivatives of ammonia. So if we go back to chapter 23, what do derivatives mean? Our derivatives are going to be where we have one or more hydrogens replaced. So my nitrogen with 3 hydrogens would be ammonia. We replace one or more hydrogens. So I can have one hydrogen replaced. This would be called a primary amine. I can have 2 hydrogens replaced. This is called a secondary amine. And if I had 3 hydrogens replaced, this is called a tertiary amine. In the cases of these, our strength is going to again depend on polarity. The more polar the bonds, so the more electrons we have focused up on that nitrogen, the better ability it has to attract hydrogens. What we're looking at here with these is that my nitrogen-hydrogen bond is going to be very polar. My R groups are going to tend to be carbons. Those are going to be less polar. And so as R increases, our overall polarity decreases. So if we were to rank these, the ammonia will be the most polar. It would be the stronger base. If I had all 3 hydrogens replaced, that's going to be my weaker base. So both acids and bases, strengths are going to depend on polarity. In the case of the acid, that polarity impacts how easily we can break the bond to hydrogen. Here, that polarity impacts how strongly we can attract hydrogens based on how much electron density is on something like our nitrogen or our oxygen or whatever that particular base is. So in this chapter, we need to be able to identify substances as acids or bases. We need to write their proton transfer equations, identify conjugates, and set up their K expressions. So on our worksheets, we are given a series of substances. So the first one we have for part 1 is a PO4 3-. So we need to identify this as acid or base. I look here, I don't have any hydrogens, and I don't have any positive charge. So that's going to tell me right away it's not an acid. I have to have a hydrogen to donate to be an acid. I do have negatives, so that means we're going to have a base. So that PO4 3- as a base, when I put it into water, it's going to take a hydrogen from the water. So we're going to increase the hydrogen in our formula by 1, becoming HPO4 3. And we're going to increase our charge by 1, becoming -2. And as we took that hydrogen off of the water, it becomes hydroxide. Now, if that phosphate anion is a base, then the water is behaving as an acid. It's donating a hydrogen. The HPO4 3- is the conjugate base of the phosphate, the conjugate acid. The hydroxide is the conjugate base of the water. So when we go to set up a K expression, we're producing hydroxide. We identify our substance as a base. This is a KB. It's going to be very important as we get into problems later in the chapter to be able to distinguish whether you have a Ka or a Kb. Part 2, we have a CH3NH2. For our acids, we're looking for hydrogens out front, indicating acidic hydrogens. There's no hydrogen out front. We look for a COOH or a CO2H. I don't have that. I look for a positive. I don't have that. So we can eliminate this being an acid. I do have a nitrogen. I have a nitrogen with only 3 bonds, which means that nitrogen has a lone pair, which means it can accept hydrogens. So this is going to be a base. So as a base, it's going to take a hydrogen from water, increasing the hydrogen by 1. So we're going to get CH3, NH3. As my hydrogen goes up by 1, my charge goes up by 1. So I get a CH3, NH3 plus. And again, hydroxide. If that CH3, NH2, so we just talked about amines. This is an amine. This is one of my ammonia derivatives. It's a base. That means water is an acid. The CH3, NH3 plus is my corresponding conjugate acid. And the hydroxide is my conjugate base. It's a base. We're producing hydroxide. We're dealing with a Kb. So my Kb will equal the concentration of CH3, NH3 plus, times the concentration of hydroxide, divided by the concentration of CH3, NH2. Next, we have a C6, H5, NH3 plus. So we need to identify this as an acid or a base. Now my bases, remember my bases could be hydroxides. There's no hydroxide here. My bases could be nitrogens, but they have to have only 3 bonds. Here I have a nitrogen with 4 bonds, which means the lone pair is occupied. It's not available to donate. So that nitrogen can't accept. I do, however, have a positive. So I do have an acid. I've got an extra hydrogen here that I can donate. So this will be my acid, making water my base. So if that substance is my acid, it's giving a hydrogen to the water. So as it gives a hydrogen away, its hydrogen will decrease by 1, and its charge will decrease by 1. So I'm going to get a C6H5NH2 as my conjugate acid. We give a hydrogen to water, we get hydronium as my conjugate acid. This time we identified our substance as an acid. We're producing hydronium. That should always be true. What I identify as a base should be producing hydroxide. What I identified as an acid going into water should be producing hydronium. It's an acid, so we're representing this by a Ka. Ka equals concentration of C6H5NH2 times hydronium divided by my C6H5NH3 plus concentration. Now looking at our final substance given, we were given an HSO3 minus. Now I have a hydrogen out front. That hydrogen is usually indicating an acidic hydrogen. So this can donate a hydrogen. But we've got to explore our entire compound. We can't just stop there. So what I've also got to notice is I've got a negative, which means I've got all kinds of lone pairs that can be donated or can accept hydrogen. I have a combination of a hydrogen that can be lost and negative charge that can accept. This is amphoteric. So we're going to need to write the proton transfer for both scenarios. So if I write the scenario in which this is an acid, as an acid, it will donate hydrogens to water, giving me hydronium and SO3 2 minus. So again, I lose a hydrogen, I lose a charge. In this scenario, my HSO3 minus is an acid, the water is a base, the hydronium is the conjugate acid of water, the SO3 2 minus is the conjugate base of that sulfite. Now if I write the scenario in which this is a base, then it's going to accept a hydrogen. So if it's accepting a hydrogen from the water, it's going to go up by 1, becoming H2SO3 and hydroxide. So where it behaves as an acid, we represent that by a Ka. So my hydronium times my sulfite divided by my hydrogen sulfite. Where it behaves as a base, we've got a Kb. So my H2SO3 divided by my hydroxide, or times my hydroxide divided by my HSO3 minus. Now, in reality, HSO3 minus is not doing both at the same time. It's doing one or the other, and it all depends on what it's interacting with and which is stronger. And depends on whether or not this HSO3 minus is a stronger acid or a stronger base. To know what it's actually doing, we would have to know the Ka and Kb values. So we would compare Ka and Kb to determine if it's being an acid or a base. So comparing Ka to Kb will determine which is stronger. Now, a couple things we want to keep in mind. So again, for an amphoterous substance, comparing Ka to Kb will determine which is stronger. For each conjugate acid-base pair, we can calculate a Ka or a Kb. So, if I look at my ammonia, for example, and remember we write our equations in the direction we are interested in. So if I'm interested in ammonia interacting with water, I'm going to write it in that direction. And that's going to produce NH4 plus and hydroxide. And so the K for that reaction is going to be a Kb because we're looking at forming hydroxide. Now, my NH4 plus is an acid. It's the conjugate acid of my base, so it can also interact with water. If I have my NH4 plus interacting with water as an acid, it gives a hydrogen to the water. It's going to form NH3 and H3O plus. So this is where we're talking about our reaction can be reversible. And in this scenario, that equilibrium is described by a Ka. Now, we can take equations and we can add them together. So if I add these, we're going to cancel things that appear on both sides. So my NH4 plus cancels, my NH3 cancels, and I'm left with 2 H2O producing hydroxide and hydronium. Well, that equation is the autoionization equation for water. So that is represented by a Kw. When we add equations together, the K for our overall equation is going to be equal to the product of K's of our individual steps. So in this case, Kw is going to be equal to Ka times Kb. We can use this particular equation to convert between a given K for a base. So for example, if I knew the Kb for ammonia, I could determine the Ka for the conjugate. So K for the base and its conjugate acid, or K for the acid and the K for its conjugate base. Now we can further manipulate this equation. I could take the negative log of both sides, which would result in getting an equation that says that my pKa, so remember P just means take the negative log, so negative log of Ka plus negative log of Kb equals the negative log of Kw. Remember, Kw is 1 times 10 to the negative 14th. We take the negative log of that, and that gives us a value of 14. So sometimes you will see your Ks, because again, they're in scientific notation, you might see them expressed in log values in order to more easily compare your strengths. And so we can convert between Ka and Kb, or pKa and pKb, using this equation.